Okay, so a few announcements to make. The first is that tomorrow's Thanksgiving. So let me just say I'm thankful for you. This has been really fun for me to give this class and to have so many people from different places come and and people paying attention and thinking about model-theoretic tree properties. So thanks. Second thing is that the class is on YouTube now. So if you go to YouTube and you type model-theoretic tree properties, you will find it. I think there's one class that's been posted, but I'm going to post it about a pace of one a day. So it'll be there in perpetuity, which is nice because these Zoom videos have an expiration date. Like when you just host them on the course page, they expire after 90 days. So now they will exist forever, or at least until the university asks me to take them down. So that is good, and you should find them there if you have any need for them. And the third thing is that we are beginning on NSOP 1. And that is a topic about which I have much to say. It was the subject of my dissertation, which was, I don't know, some 200 pages long. But obviously, because we only have like 1 week to talk about it, the presentation here will be much condensed. But as it happens, I just finished 6 weeks of lectures on this topic, and that concluded this morning. And there are lots and lots and lots of notes. So those notes are all available on the Fudan Logic Groups page. And I'll add a link to the course page on the CCLE website. And so if people, for whatever reason, have further interests in checking out the details of the things that we don't do, almost everything in SOP1 that we know is contained in those notes, and they're presented in a pretty clear way, I hope. So that is something to think about if you're unsatisfied with the depth in which NSOP1 is discussed here. All right, so before we start on NSOP1, I think we should just sort of wrap up our discussion of NTP2. So let's remember what we proved last time. So last time we showed a few things. So one is we showed that if phi x, so okay, let's suppose T is in TP2 and M is a model of T. So if phi xa, if phi xa divides over M, this is witnessed by any strict invariant Morley sequence so let me give myself some more space. AI I less than omega over M with A0 equals A. So if you have a sequence that begins with A and is strict invariant, then that will always witness the dividing of that formula. And that is like Kem's lemma, right? Because Kem's lemma says that a formula divides if and only if it's inconsistent along every Morley sequence of a particular kind. Now, let's remember what strict invariant means. So you had some notion of a strict invariant global type, and that was like invariant one way and forking, non-forking another way. So you have some global invariant type, so that if you realize it with an element A, so let's just write it. So you have some global type Q, you realize it with A over a set B, then that should imply that B is non-forking independent over M with A. So this is like some way of arranging a symmetric situation. All right, so that's the first thing we did. And the second thing we did is we proved that if P is a type over the model, then P has a global strict invariant extension over M. So this was the hard part, actually. So the proof of number one was really just observing that, okay, if you realize a Morley sequence in a strict invariant type, then you can arrange to have an array where the paths are Morley sequences through your type, and the rows are indiscernible sequences which witness that the formula divides. So if you were consistent along a Morley sequence in your type, then you would be consistent along every path through this array. The rows would be k consistent for some k, and that would give you TP2. So that was really, really easy. We were just pushing against the array. The harder part was this existence argument, and that was where we proved a lemma called the vacuum cleaner lemma, which had this funny statement. It said if you had some global invariant partial type, and it implied a disjunction of a formula and a disjunction of formulas that divide, so a formula and a formula that forks, if you will, if the parameters of the formula and the formulas that fork are invariant independent, then the type has to imply the first formula, not the forking formulas. So as a consequence, you can prove a compactness argument that says that this invariant type exists. So that was like the complicated part. All right, but then this has as a corollary the following fact, which is that if T is in TP2, then for all M, which is a model of the theory, if phi xa, or let me say it this way, phi xa divides over M if and only if phi xa divides with respect to all strict invariant Morley sequences over M in the type of A over M. So because we know that those sequences exist, this is something non-trivial and in fact quite useful. And okay, let's just recall one of the corollaries. So I won't give all the details, but it's worth seeing. So forking equals dividing. Over models in TP2 theories. Okay, so how do you prove that? Well, you just suppose phi xa forks over M. So phi xa implies some disjunction of I less than k, ci x. Let me write it this way, bi, where each ci x bi divides over M. And then what do? You just let ai be, I'll write it this way. I'll write like 1 comma I, b 2 comma I dot 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 b k minus 1 comma I, as I ranges over the natural numbers, be a strict invariant Morley sequence over M with A0. Sorry, this should have started at 0, I suppose. It's a bit annoying. So 0, 1. All right, so like b0, 0, dot, 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 b k minus 1, 0. That should be equal to a, b0 through bk minus 1. So you take a strict invariant Morley sequence that starts with all the parameters in sight. Then you know by invariance that if I look at phi x ai, I less than omega, that has to imply the conjunction over all I less than omega of the disjunction over, let's say, j less than k of c sub j x bj comma I. So if you realize something on the left, then for each one of those natural numbers, you have to pick one of the disjuncts. And that means you have to pick the same disjunct infinitely often. And so by the pigeonhole principle, if you can realize something on the left-hand side, you have to realize something on the right-hand side infinitely often. But because we know that these are all inconsistent along a strict invariant Morley sequence, all of those sets are inconsistent. So that's a contradiction. So by the pigeonhole principle, we conclude phi x ai, I less than omega, is inconsistent. And what does that tell you? That tells you that phi xa divides, because the sequence that we constructed witnesses it. So this is exactly the same argument for forking equals dividing in simple theories. The only thing that has changed is that we have to work with strict invariant Morley sequences instead of Morley sequences. And we know that we can because we proved that those exist. So that's it. That's it for NTP2. Okay. Are there any questions about NTP2 before we move on? No? All right. So basically, the thing that we did when we were talking about simple theories was we were focused largely on the results that were proved in Byung-Hun Kim's thesis, which I believe was finished either in 1996 or 97 or something. So, mid-90s kind of stuff. Then the stuff that we just talked about in this like NTP2 section was stuff that came out of Artem Chernikov's thesis. So that's stuff that was much more recent, things that were discovered, I guess, right around the time I was entering graduate school. And the stuff that we're going to talk about now with respect to NSOP1 was stuff that I worked out with many people in graduate school. So this is extremely recent. So now we're moving on to NSOP1.
Hey, Nick, can you hear me?
Yeah.
Oh, okay. So just, I do have a question about NTP2.
Sure.
But not a technical one. What open problems or conjectures
Great.
are there
So,
still?
yeah. So I think there's some nice questions about NTP2. So one of them that I like, let me write it down. So there's a version of the property which is called distal, or sorry, no, not distal. Oh, sorry. What is it called? It's called what is this? I've forgotten the name. Resilient. Sorry, there's a notion of a resilient theory, and I'm not 100% sure I can tell you what it means, but I think it's something like you have two indiscernible sequences. Okay, so check me on this, but I think that the definition is something like you've got two indiscernible sequences, AI, I in Z, and so this one is indiscernible, and then you have BI, I in Z. This one is A not equal to 0, indiscernible. And you have A0 equals B0. So it looks something like a cross. So this one is like the A bars, and this one is the B bars. And your rule will say that, okay, phi x AI, I in Z is consistent. And phi x BI, I in Z is K inconsistent for some K. So this is what it means to be not resilient. So if there's no such phi, so we say T is resilient. So you should check me on this because I haven't thought about this notion in a while, so I might have gotten the definition a little wrong, but I think this is fundamentally the idea. And then there's a question of whether or not resilient equals in TP2. So this is one question, which we can call Q1. Question 2, which I think is really interesting, is burden subadditive? Which we've mentioned before. So we proved actually that burden is submultiplicative. That, you know, if you look at a type in, say, a few, you know, in two variables, then you can sort of get a bound on the burden of that type in, say, two variables by looking at the product of the burden of types in one variable that come from looking at realizations. So that's a thing you can do. But in fact, for many of the applications of DP rank, what you use DP rank for is I mean, you use that it's additive in an essential way, subadditive in an essential way. So there are a lot of sort of things in model theoretic algebra where DP rank is used. People would like to generalize that to INP minimal case, and they can't because there isn't like a good notion like DP rank available in this context. That's because we don't know that burden is subadditive. If we knew that, then a lot of things would become possible. And then I think there's a third question which is interesting to me. So there's something called the SOPN hierarchy. I don't know if you have heard about this. So the question is the SOPN hierarchy strict in TP2 theories? And there's a related question which I'll call Q4, which is okay. Let's recall Shaw's theorem, which we proved in this class, which said that if you have the tree property, that happens if and only if you have the tree property of the first kind or the tree property of the second kind. We proved that a long time ago. And recall that this was somehow a version of this other theorem that says that if you have the order property, if you're not stable, that happens if and only if you have the independence property or SOP. Does anyone remember that? We proved these two theorems. So here's a question. Is it true that the tree property is equivalent to having either TP2 or the strict order property? So if this were true, this would be like a kind of radical like generalization of what Schella had originally proved, because you know, like if you're in an NTP2 theory that is not simple, must you have an order around? I mean, must you have a definable or like an interpretable partial order with infinite chains?
Wait,
That
can
would
you
be
repeat the last sentence? If the
uh,
infinite
yeah.
of the
So
open.
is it the case that in every not simple NTP2 theory, there must be an interpretable partial order with infinite chains? That's equivalent to this statement.
Yeah. Okay. Thanks.
Yeah. So that's open. We don't know a single example, and you know, it would blow my mind if that turned out to be true, because that would just be like so much structure coming from very little. But I mean, having like orders around, I mean, that's a kind of.
And you think this should be very hard?
It depends on how it goes. So I mean, it could be that you can write down an example. You find a simple example that
No.
everyone had missed.
If this is true, if this is indeed true.
I don't know. You know, so I think the proof that TP1 versus TP2 are, I mean, so the proof that the tree property is equivalent to TP1 or TP2. The proof of that, as you recall, is you just take a witness to the tree property, you make it very indiscernible, and then you observe that it witnesses one of these two. And of course, there's some analysis you have to do to find it, but it, you know, you just make it indiscernible and you find it. I think there's probably going to be some kind of, I mean, if this is true, then there has to be some kind of clever change. You know, you have to work with something more complicated than just the indiscernible trees that we've looked at. But that's not to say that it necessarily is hard. It could just be that there's something simple and elusive, and with the right insight, then you would see it. So I don't know. I'm not prepared to say it's going to be difficult. A lot of the things in this corner of model theory are really about cleverness more than they are about like.
How many or how much people are thinking about these things? I mean, it can be the case that many smart people think about these things and fail, and it can be the case that everyone expects that it's to be hard and doesn't even try much.
Yeah,
Like,
I mean, okay, Shella thought about it, so that's like, that's equivalent to roughly 200 people thinking about it. Um, but like there's still sometimes there's news. Like just this past week, there's news that there's a theory that's supposed to have SOP2 and not SOP3, which had been an open problem for a few decades. This is a recent theorem of Masoud Permani and Ali Valizadeh. So I mean, if provided that the example checks out, that there's news and people had thought about that for quite a long time. So you just don't know. Um, yeah, and I think either way would be interesting, right? Yeah. So all of you should think about these problems. This is homework.
okay,
Any
thanks.
other review questions before we move on? No? Okay, so now let's move on to NSOP1. So brace yourself. You're about to see the strangest definition of this class. So definition. So suppose phi xy is a formula. We say phi has SOP1 if there is a collection of tuples indexed by the full binary tree, so by 2 less than omega, such that two things happen. Okay, so the first is like all of the tree properties we've studied so far. You say paths are consistent. So for every eta in 2 to the omega, phi x a eta up to I for I less than omega is consistent. Okay, so this one is familiar. And here's where things get a little funky. So suppose you take two nodes which are incomparable, but in a particular configuration. So eta will extend eta meet nu in the 0 direction, and nu will be equal to eta meet nu in the 1 direction. Okay. Then so if this, then phi x a eta phi x a nu is inconsistent. All right, so let's draw a picture of, sorry, let me zoom out a bit. Let me draw a picture of what this looks like. So you've got some binary tree. Like so. And okay, we're familiar with paths being consistent. This is a picture that we've seen many times. However, what we're saying is, suppose I take a node like this thing here, this node here, and I take anything here. So if I take anything here inside this cone that I've drawn, what is its meet with this node? Like, let's label this, let's call it nu. So if I take eta anywhere inside this cone, what is the meet of eta and nu? That would be the empty node, right? This node here, which is eta meet nu. And this node here is equal to eta meet nu concatenated with 1. I'm thinking about this as being the 1 direction, this as being the 0 direction. And this node here is eta meet nu concatenated with 0. So anything that extends eta meet nu concatenated with 0 together with eta meet nu concatenated with 1 give me two nodes that are inconsistent. But that's the only time that I say anything about when things are inconsistent. So for example, I could take a node here and a node here. and those could be consistent or not. I haven't said anything. I'm agnostic about whether or not they're consistent or inconsistent. I've only insisted that when nodes are in this very strange configuration, then I'm forced to make them inconsistent. So that is what it means to have that is what it means for a formula to have SOP1. And then we say T has SOP1 if some formula does. Otherwise, T is in SOP1. Okay. So that's our definition. And I've said this many times, but I remember I got started working on this property in graduate school because there was this interesting sort of theorem of Byung-hun Kim. So Kim, in a paper called Simplicity and Stability in There, proves that the independence theorem over models, the one that we proved, will fail for any theory that has TP1, assuming that you have a measurable cardinal. So if you have a measurable cardinal in the universe larger than the size of the language, then you can prove that the independence theorem over a model will fail in any, provided that your theory has TP1. Now, why did you need that measurable cardinal around? You needed it because, you had to extract indiscernibles. So you had to do something like what we did with Erdős-Rado. But if you sort of change the argument a little bit, then you could get rid of the measurable cardinal. And so Artem in his thesis observed that you could get rid of the measurable cardinal. And then when Artem and I started working together at the beginning of graduate school, he had sort of observed that you could use the Kim-Pillay theorem, which gives a kind of criterion for when a theory is simple, to modify it in such a way that you got a criterion for when a theory is in TP1. And then I just sort of observed, as what I thought was just trivia, that you could also prove that that argument went through, just assuming SOP1. So SOP1 is weaker than TP1. Now, what does TP1 say? It says that all incomparables are inconsistent. Now I've said something weaker. I only said that incomparables in some weird configuration are inconsistent. That's obviously a weaker thing to ask. So it was like interesting piece of trivia that you just needed this weaker property, which had been defined in the literature already, in order to get this non-structure result, to prove that the independence theorem failed. But then what was kind of bonkers is that slowly we started observing that, in fact, the failure of the independence theorem was equivalent to SOP1. So that turned out to be kind of the right hypothesis. And this phenomenon happened sort of several times. We would make some natural conjecture about something we expected to be true for NTP1 theories, and it turned out to be true for NSOP1 theories, and in fact to characterize them. So then the project just sort of blossomed from there. But that never really answered the question of why this property was defined in the first place. So the first place that this appears is in a paper of Mirna Jamonia and Shala, Sahar and Shala, where they define it. They observe some of its implications with other properties, but then they don't prove any substantial theorems about it. So I was always very curious. And I remember when I was in grad school, there was something called the Boise Extravaganza in Set Theory, which was in San Francisco. And Mirna Jamonia was speaking there. So I went and I asked her, okay, why was this property defined? And she says, well, I'm not really sure. Perhaps you should ask Saharan. And then a year after that, I went to Jerusalem and I met Saharan. And so I asked him again the question, and he said he forgot. So now we just don't know. We just don't know where this property comes from. It was sort of given to us by some alien force, and we just have to reckon with the fact that, we're thankful that we know it. Great, but so this is what we're going to study. But as it turns out, there is a way of reformulating this property, and I don't know that it looks so much more natural, but it turns out to be something you can really work with, which is a fact that we will not prove, but we will state. If we had time, I wish we could have proved it, because I think it's actually quite in keeping with the arguments that we've been doing. You play games with formulas and things work out. So what's the fact? The fact is that T has SOP1 if and only if there is an array CI0, CI1, I less than omega, and natural number k less than omega, such that three things happen. So the first is that if I look at the zero column, oh, I should also say and phi. So the zero column is consistent. So if I look at ci0, I less than omega, this is consistent. Okay. B says that if I look at the ones column, that's going to be k inconsistent. And C will say that ci0 has the same type over everything that comes below as ci1. And that's for all I. Okay, so this gives us a kind of linear configuration. Now we don't have to think about the tree. We can just think about this sequence of pairs of tuples. So what does this look like? You've got one column here, and you've got this other column here. And I'm going to draw it this way for reasons that will become clear, hopefully, in just a second. Where if I look at this column, this is consistent. But notice, for example, that this point and this point have the same type over everything that comes below. So in particular, I know that, say, this point, this point, this point, and this point are consistent. So it follows that this point, this point, this point, and this point are consistent because they have the same type over everything that comes below. So in particular, this has to hold. Moreover, let's suppose for a moment that k is 2. So we're told that this column is k inconsistent. Let's suppose, just for simplicity, just to get our intuitions going, that this is 2 inconsistent. So because I know that, say, this point is inconsistent with this point, it follows that this point is inconsistent with this. So, and in fact, anything above it on either side. So we get lots and lots of things. So I'm going to draw the picture like this. And the reason that I draw it like this is because you can think about this as somehow coming from a tree. So if I'm given this picture, let me get rid of this color for a second. So if I'm given this picture, what I know is that, for example, there's an automorphism that takes this point to this point. So using the automorphism, I can just see where does it send the rest of the tree, or where does it send the rest of the array. So it's going to send it somewhere like that. Okay, so what do I know now? Well, I knew that this point was inconsistent with everything up here. And so it follows that that's still true. And also, like, this point is going to be inconsistent with everything up here. And I can continue this construction, right? There's an automorphism that takes this point to this point. So I can copy and see where it sends the rest of the tree. And I could do the same thing here. There's an automorphism taking this point to this point. So I can copy like that. So why do I know that there are such automorphisms? Well, that's where I use this third condition that says that ci0 has the same type as ci1 over everything that comes below. That tells me that there are automorphisms that do this. And so using this, I can inductively construct a tree using many automorphisms that satisfies exactly SOP1, assuming that k is 2. So when k is 2, it's actually pretty, it's a bit harder than an exercise, I would say, but it's very doable using many automorphisms to construct the SOP1 tree. And then what's tricky is to try and get k down from some arbitrary natural number to 2. So you need to play games with the array, but you can do it. Okay, And then to go the other way, you just sort of take your witness to SOP2 to, or sorry, SOP1 to be a very big tree. And you can sort of find this array sitting inside using the pigeonhole principle to find things that have the same type. So I won't give this construction because I think the more interesting stuff involves the theory of independence, connecting this to like forking and dividing. But okay, this is sort of the key fact on the syntax side of INSOP1. All right, so now I want to come to the central definition, which is that of Kim independence. So let me label this. So Kim independence. So here's a definition. A formula phi x a. So I'm only going to talk about Kim dividing over, or Kim independence over models. So I'm going to fix a model over of my theory and only talk about dependence or independence over models. So let's imagine that we fixed an arbitrary one and talk about what it means there. And I'll describe why in just a moment. So a formula phi x a, Kim divides over M if there is a global M invariant type Q, which extends the type of A over M, such that for some, equivalently all, Morley sequences over M in Q, let's call it I, which is like I less than omega, which realizes Q tensor omega over M, phi x ai I less than omega is inconsistent. So what does this say? What this says is that a formula Kim divides, if it divides, and that dividing is witnessed by a sufficiently generic sequence. So this is Kim dividing is the dividing that is witnessed by Morley sequences in global invariant types. Okay, so one slogan that we often use is that Kim dividing is like dividing at a generic scale. So it's the dividing that happens to be witnessed by Morley sequences of a certain kind. Okay, and then using this, you get the normal definition. So you say a formula Kim forks over M if it implies a disjunction of formulas that Kim divide over M. So this is just like the way we defined forking in terms of dividing. We will define Kim forking in terms of Kim dividing. We'll say a type Kim forks or Kim divides over M if it implies a formula that does. And then we get a notion of independence. So we write A is Kim independent over M with B to indicate that if I look at the type of A over MB, this does not Kim divide. Sorry, Kim fork. It's not Kim fork over M. Okay, so this notion comes from Kem's lemma, and it also comes from Byung-hun Kim himself. So there's a sequence of conferences that happens roughly every 3 years. I guess since since either 2006 or since 2009, I'm not sure, but these are the neo-stability meetings. And I don't know, to my mind, they're some of the most, they're basically the nicest meetings we have about pure model theory. So most conferences have some mix of applied model theory and pure stuff, and that's great. But it's nice to have something which is just for pure model theory. And this neo-stability meeting is something that happens every 2 years, and it's sort of developments in IP, simple theories, whatever else, in TP2, so on and so forth. And in 2009, Byung-Han Kim, whose name has been attached to a lot of the things we've talked about so far, sort of gave a pretty speculative talk where he was speculating about what a structure theory for in TP1 theories might look like. And he proposed a notion of independence that said that a formula, it's not exactly what he said, but it's sort of close to what he said. He said that a formula should divide in his sense. I think he called it strongly divide, if it divides with respect to every Morley sequence in the parameter. So in a simple theory, that's the same. So Kim's limit tells you that if a formula divides, it divides with respect to every Morley sequence. So you could just take it as a definition and try to understand that independence notion in TP1 theories and see if it gives you anything. So we had to make a bunch of changes to that definition to get something to work, although it turned out to be about right. But basically, if you change the notion of Morley sequence to being invariant Morley sequence, and you work in SOP1 theories instead, you basically recover Kim's notion. So that's why the notion of Kim dividing is named after him, because it's like inspired by something that he suggested, but also it relates in a concrete way to Kim's lemma, which is something that we're going to do next. So what I would like to do, and I think we probably won't finish, but maybe we can do one direction and then try to finish next time, is the following. So this is what we're going to call Kim's lemma for Kim dividing. And this is the following. It says that T is in SOP1 if and only if for all models of your theory T, phi xa, Kim divides. So, okay, T is in SOP1 if and only if the following statement is true, which I'm going to write in parentheses. For all M, which is a model of theory, phi xa, Kim divides over M if and only if, I don't know why I'm switching my notation, if and only if phi xa divides with respect to all Morley sequences in M invariant types over M, extending the type of A over M, or starting with A if you like. So like in the parameters. So why is this Kim's lemma? Well, one of the things that Kim's lemma says is that it changes this existential statement, there is a sequence that witnesses dividing, into a universal one. Now here, we're not talking about dividing in its fullest sense. We're restricting our attention to the kind of dividing that is witnessed along some Morley sequence, but we still recover this quantifier exchange, right? What does it mean to Kim divide? It says that there is some Morley sequence along which the formula is inconsistent. And now we've changed that to something universal. We've said, actually, for every Morley sequence, you get something inconsistent. That's a kind of Kim's lemma. And it plays a role in the theory exactly analogous to the role that Kim's lemma plays in simple theories. So this is going to be Kim's lemma for Kim dividing, and it's going to characterize in SOP1. So I think we probably don't have time since we only have 4 minutes to do it. But what we'll do next time is we will review these definitions. We will give this proof, and then that will be one class period. And then we will do probably 1.5, maybe 2 class periods proving that this Kim independence notion that I defined here is symmetric in NSOP1 theories. So I think that's really far from obvious, and the proof is much harder, in fact, than the proof of symmetry in simple theories. And the ingredients are going to be a kind of complicated induction on ill-founded trees, which is characteristic of much of the theory of NSOP1. So I think you'll get a flavor of how the arguments go if you see that proof. But then much more is true. So this notion of Kim independence in NSOP1 theories turns out to satisfy the independence theorem, satisfy transitivity, to satisfy local character. So much of the things that you care about in simple theories hold. We won't have time to do all of those things, but I think you'll get a flavor of how the arguments go. And so that will be the subject matter of next week, which is week 9. And then week 10 will be all about NTP1. And I think we will prove a theorem about higher formulas there, which hopefully will be interesting. So that's the goal. Are there any questions?
I have an opinion question.
Sure.
So a lot of people really don't like the name NSOP1.
Yeah.
Is there actually like a subtle justification for it being NSOP, or is it just bad?
Well, no, I think the full justification that was given was just that you had the SOP in hierarchy defined for n greater than or equal to 3. And SOP1 and SOP2 sat in the right place with respect to this hierarchy, meaning so in general, SOP3 is implied by SOP4, which is implied by SOP5, and so on and so forth. And SOP3 implies SOP2, and SOP2 implies SOP1. And so they fit in the right place in the hierarchy. And also somehow the definition of the SOP in hierarchy only makes sense for n greater than or equal to 3, because if you just copy the definition, then for n equals 2, it corresponds to the order property. And for n equals 1, it corresponds to having an infinite model. So okay, I mean, you already have a name for one of those and the other one is not interesting. So, well, I mean, it's nice to have infinite models, but that's sort of like the sine qua non of the model theory that we're doing. So you don't need another name for that. So that's really the justification for why this name was picked. They just sort of sit in some place. So you're exactly right. It doesn't seem to be a well-chosen name. There were some suggestions on how to change the name. So Byung-hun Kim had proposed calling these subtle theories because it starts with S and ends in LE, like stable and simple. And I don't know. I wasn't brave enough to stick to it. I mean, like I think when I started writing papers about NSOP1, if I had called it subtle, then it would have stuck. I think I think it could have happened because, if there's a critical mass of literature that calls it subtle, then people just start going along. But model theorists love to complain about nomenclature. Like, I don't know, like every time I've been to a conference, like people are complaining like, there's so many n's, and then you have like n dependent, which means like a number instead of not dependent, and blah, blah, blah. And I just really thought, well, I'm happier with the present situation in which all of this angst is directed at someone that's not me than a situation in which I have to listen to all these complaints about why subtle is a stupid name or something. So I decided just to stick with it.
I mean, it's not necessarily too late, right? People are still trying to change NIP to
Shatterproof.
Independent. Oh, Shatterproof.
Yeah. So I like my advisor Tom Scanlon really liked the name Shatterproof when I was in graduate school, but yeah, I don't know. I think NIP is here to stay. Like, people have, like, Shaw has written many papers about dependent theories, but I don't know that that's. I mean, if you say it, then people know what you mean, but I don't know that people.
Well, so I don't like it for the same reason that I don't like simple, because it's like a word that you would use in just regular speech while talking about stuff. I mean, like you said, like the phrase "for the sake of simplicity" in today's lecture, and you didn't mean it in the technical sense. You meant it in the informal sense.
No, and of course it gets especially confusing when you do simple group theory, because if you have groups defined in a simple theory, it's natural to call those simple groups, and that's bad news.
There's a notion of stability in Banach space theory, so that's great for continuous logic.
There's also a notion of stable group.
Oh yeah.
Right. So so it's all bad, but it's also I'm not responsible for it. So complain to someone else, this is, yeah, I mean,
No, I just wanted to know, really, I just wanted to know if Gabe was wrong about complaining about NSOP and NSOP2, if there was really like a really like subtle highbrow way of looking at it where it's like, oh yeah, that's definitely the right way to think about it.
no, there's no, I think.
Because Gabe advocates that it's not a problem that NSOP1 is finite NSOP1 is finite models and NSOP2 is stable, because it's like, well, I mean, those are very natural properties.
I mean, that's true. Those are natural properties, and in a way, I mean, I guess it naturalizes the SOPN hierarchy. But I mean, okay, the SOPNs make sense to me, right? I mean, because you have a formula that witnesses the order property, and then you're omitting larger and larger loops, which I mean, so if you have an actual order, you omit loops of any size, right? Like if you have a transitive linear order, then of course you can't have x is less than x1 is less than x2 is less than x3 is less than x4 all the way up to xn less than x0. You can't do that, right? You can't loop around at any size. So having these bigger and bigger approximations tell you something like you're getting closer and closer and closer to a linear order. So for that, I think the SOPN is like a fine name. It's like the order property plus something, and what is that plus? It's getting you closer and closer to the strict order property. So that makes sense. But I think SOP1 and SOP2 are defined very differently. They have nothing to do with orders, really. They just sit in the right place in the chain of implications. And I think that's the only justification I think there is for the name that was chosen.
I mean, you could say the same thing about like simple and super simple, right? Like they also sit in the chain of implications the same way, don't they?
Sure, that's also true.
So I had a real question too. So the conjecture about, or the question about order property if and only if TP2 or SOP.
No, it was tree property.
Tree property. And the tree property is, I'm trying to place this on the map on forking and dividing.
So having the tree property is the same thing as being not simple.
Simple. Okay.
So simple theories are exactly the theories without the tree property.
Right, okay. So a counterexample would be in like the lower right, like the empty box. Like I don't know if you.
No, I think it would be in the. Oh yeah, you're right. It would be in the lower right because it would be in SOP.
Yeah.
And the lower right quadrant is the unstable NSOP theories.
Yeah. I mean, I was just looking for like empty boxes because I was under the impression that Gabe was pretty like all the like categorizations there are known to be, or I guess no, they're not all known to be strict because there's empty boxes. Anyways.
Yeah, this is a big empty box, but also, I mean, the SOPN hierarchy is not known to be strict in TP2 theories. So it's not known if you can have an SOP3 theory, which is in SOP4 and in TP2, which is a related. I mean, of course, the answer to one implies the answer to the other, right? Like if you know that if you're in SOP, or sorry, if you're not simple in TP2, then automatically you have SOP, then you have SOPN for every n. So the hierarchy is not strict, but perhaps the hierarchy could be strict. In which case the answer to the other question is no. So one of the questions answers the other.
Okay.
Wait, not quite. Maybe you can be not SOP, but also SOPN for every n.
Yeah, no, certainly. So I'm not saying these questions are equivalent. I'm just saying that one of the questions answers one of the others. So
yeah, one direction only.
You have a one direction implication. That's right. If the hierarchy is strict, then of course, being unsimple in TP2 does not imply SOP. Because the hierarchy being strict in particular means that it wouldn't imply some SOPN. All right, so I should probably go to my discrete math class, but
actually, Nick, I did have another question.
Go ahead.
No, probably we won't have time now, and probably it's not the right time anyway. But I don't just don't want to forget it. So the question is, what happens if you combine the definition of Kim independence with strict invariant
Yeah. So I
Morley
think I
sequence
mentioned this to you
independence?
in the mini course that Alex Kruckman and I are writing a paper about exactly this topic, where we look at what we call lax invariant Morley sequences. Where so what does it mean to be strict invariant? It says you're invariant one way and non-forking the other way. So define a variant of this where you say strict one way and Kim independent the other way. Okay, so this is like a weaker condition, and we can prove that actually in any theory, such sequences exist, and then you can look and you can ask, okay, what are the theories in which you have a Kim's lemma for those kinds of things? So this simultaneously generalizes the Kim's lemma in TP2 and the Kim's lemma in SOP1, and we know we have examples. So for example, if you look at parameterized dense linear orders or like infinite dimensional vector spaces over real closed fields with bilinear forms, and probably certain unbounded PRC fields. I mean, so a lot of nice examples. These will satisfy that. And on the other hand, if you look at certain pathological combinatorial examples, like the triangle free random graph, that doesn't satisfy that. So we know that at least has content. But what we don't yet know is what would be a kind of syntactic characterization of this property. So that's something very much.
Yeah, that was my next question. One of them. The last when I asked it before, I didn't know what strict invariance is anyway. So
I see. Yeah. So now you know. Good.
Can you remind me the NTP2, the Kim's lemma? You have the equivalence of with regular dividing, but do you also have that the equivalence of existent for all implies NTP2 without the dividing part?
Yeah, basically, I mean well, so okay,
if
I
you
think
just
like,
omit the equivalent with the usual dividing, like you do with
yeah, so
NSOP1.
the equivalence of those two things doesn't characterize in TP2 because, for example, that holds in the SOP1.
Oh,
Kim
for strict invariant.
Still, right? So I mean, so in particular in SOP1 theory, if you divide
okay, right, yes, of course.
strict invariant, then you divide with respect to all.
So what happens if you take this as a definition? I mean, in analogy to NSOP1.
Yeah, so the problem is that you don't know that these exist always. So I mean, okay, in any theory, there are always models in which strict invariant Morley sequences exist, but you don't know that over every model they exist in every type. So this gets kind of subtle. I mean, the existence issues are really the problem, but I think you're exactly right that this Kim's lemma probably characterizes the same class. In the situation in which it exists, that for all should imply exists, or sorry, exist should imply for all.
Which class?
The one that I was just describing, the one that satisfies.
Oh, okay, the Laxi, the one with the Laxi.
Yeah, I mean, my guess would be that this actually characterizes the same class, but I don't know that for sure.
Okay, thanks.
Okay, so now I definitely do need to go, but I hope everyone has a lovely Thanksgiving, and I will see you all on Monday of next week.